Welcome back. And those of you on YouTube, like and subscribe? No? Anything else I should tell them? Did you know that Lisa Hoffman has a little bit of secret merch in YouTube? I don't know if you know this. I have one. I made one for her. Yeah, the garbage day. I was thinking of making stickers because those are cheap and you can hand those out. Oh, I would love it. I would love it. I would love it. So yeah, for those of you on YouTube, Lisa Hoffman, lisahoffman.com. We always joke. So when we have our evening conversations about statistics, it's called dinner. We usually joke about like we're not really YouTubers, even though my son really wants us to become that. But we got to like act like it, right? So yeah, merch. For her birthday, I think last year or the year before, I got her a shirt that says "Happy Garbage Day." So I was like, yeah, the one piece of merch she has. I mean, limited edition, unique. Yeah. I think the like every shirt I order online, it fades after you wash it a couple times. Yeah, and of course I didn't pick the right stuff. Anyway, welcome back. We're back to path analysis. Thank you for coming back. Thank you for watching. This is we're going to finish the lecture we left off with last time. But before I start, I wanted to start by just announcing. So today, finish path analysis. Start on confirmatory factor analysis unless something goes awry or we need more time on path analysis, which is fine. We'll do that. The longer we take, the fewer homeworks there are. There is incentive to stall for all of us, right? Fewer things I have to prep, fewer things you have to do. Let's just explain path analysis really well. No, yeah, that's right. I like standing over here. I think this might work a little bit easier, of course, until I have to run R and then I'm stuck. But hey, come on in. So path analysis today, we left off last time. This was our model, if you remember that. This is our flow chart on how to do path analysis. But I guess I should stop and say, do you have questions for me before we begin? Yes.
So about the model,
Yeah.
there was like variance, multiple widths,
Mm-hmm.
and then from the output table in R, I remember there are two columns.
Yes.
Standard and scale.
Yes.
And I don't exactly remember which.
If you see scaled, use scaled, always.
Is that the most more like robust?
That's the more robust, that's right. And so what happens is that column, and again, I'm trying to teach this class in a way that doesn't bog you down on all the technical details, but the robust estimation, robust maximum likelihood is built with the idea that if you have data that have too thick or too thin tails, right? Everything we've done up this point is assuming normal distributions. But if you don't, if they're still symmetric and unimodal, but lepto or platykurtic is what we call it, too thick or too thin tails, it's supposed to help correct for that issue. And so but here's the fun thing about it. If you use robust, if you don't have lepto or platykurtic data, if it's truly normal, then it doesn't adjust anything. That scaling factor that you're estimating would be 1, and so it doesn't rescale any of the statistics. It just stays the same. So when you use the scaled column, in the best case scenario, you don't need it. It's identical to the not scaled. But more practically speaking, it should be the one that you use because robust estimation seems to be a little bit more effective at being accurate. So, good question. Yeah, there's a lot of output. A lot of output. And Levon's interesting. It gives you both. M plus only gives one set of statistics. You have to pick the estimator, and then it just gives one. But Levon has both. And yeah, it just adds the confusion. So thank you for the question. Other questions? I'll take the silence to be meaningful. Let's begin. The final path model. My son, by the way, he's 10, and he loves the song The Final Countdown from the 80s. And so it's amazing, right? I mean, I know, no, actually, most of the people my age can't stand it because we've heard it all of our life almost, right? But interestingly, I was in Germany last year. I'm on a train I was in Mannheim. I was trying to get to Frankfurt to get to the airport, train in the morning, hop on a car, group of soccer kids, like a soccer club comes on, football, and they're all about his age. And they're, playing with their cell phones and whatnot. And they're blaring on repeat at high volume, the final countdown. And I'm like, doesn't matter what country we're in, we're all the same, right? So maybe the final countdown, the final path model. Let's go. That's where that came from. All right, and I'm not going to sing it for you. And if you don't know the song The Final Countdown, you got to go look that up on your own. That's it. You don't want me singing. My teaching evaluations I care about, and I know if I start to sing. All right. Let's see. All right, so this was it. We went through, just kind of going through our notes here, we went through and actually, Michael, I am going to have to do the slideshow, I think. So this will be easier. No, it. Got nothing. All right, so I'm going to stand over here. No problem. Trackpad works. You know, that's the funniest thing. The thing that sets me the weirdest sideways about any computing device is if the input doesn't work. It's like, that's the most basic thing, right? That's the most basic. We've been doing this for, I mean, large scale since the 1960s. Right? Get your input to work. Anyway, yes. I'll quit freaking out in front of you here. You don't want to. Well, Lisa may have her tics. Mine is I scream at technology. I'm trying not to do that for you. Okay. So we went through, the whole thing's not working now. Okay, here we go. We went through, and we saw that the model fit for our model wasn't ideal, right? We fit the model. We saw model fit. We had a CFI estimate of, here, let's just take a look, 9.918. Again, this is the scaled column. Sorry for the size of the font, but 0.918 right here. I'll make this a little taller. Okay, and then we want this to be what? Anybody remember? The CFI? What's ideal for? That's it. And 0.95. The TLI, we want 0.95 or higher. Didn't work. The RMSEA, we want 0.08 or lower. Actually, ideally 0.05 or lower. That's not happening. And the standardized root mean squared residual looks pretty good. Close to where it needs to be according to some standards. Well, it's just the last one. So we saw all that. And then what is wrong with my slides? We're going to fix this. Kiosk mode, that was the problem. Because if I do this, there we go. All right, so we saw that we went to the modification indices. Sorry, before we did modification indices, we looked at the residuals of the covariance matrix, right? Now, this is different than your residual, again, in linear regression, the E at the end of the line, right? This is the difference between what the saturated model's covariance is. Remember, saturated is basically what you see in your data if you were just to get an estimate of covariance, and comparing that with what the model thinks it should be based on the model parameters. These are normalized, meaning we interpret these like z-scores, so anything that's plus or minus 2, or even plus or minus 3, something that says it's quite a way away from 0 in a statistical sense. So here we had two elements that were sort of highlighted, one that was 5.051 between math self-concept and perceived usefulness of math, and one between gender and college credit hours that was negative 2.56. And I had this big disclaimer saying, I'm just the stat guy. Sorry, I just do data science. I don't do theory. But no, really, technically speaking, there's lots of artifacts of numbers that can happen here, right? So we'd like to have a theoretical basis for making modifications. At that point, we said, okay, let's go to the modification indices to see which parameter may help us the most. And there's three. We're focusing first on that big cell, the usefulness math self-concept residual covariance. We want to correct that. Right? So there are three different parameters that would relate to that cell that involve both usefulness and math self-concept. And last time we found this would be the residual covariance. Right? This is the undirected arc if you're putting it on the path diagram. This is basically saying, yeah, our residuals for both of these have a relationship, but we're not explaining why that's there. It's just a relationship. Whereas these other two, usefulness being predicted by a math self-concept or math self-concept being predicted by usefulness, implies a much stronger set of sort of hypothetical causation that's at place. Now, again, this is all observational data. This is all simulated data. So technically, there is a causal order to it because I simulated it. But in real data, we wouldn't know the causal order. But this is basically changing a regression equation to add a predictor to it. So it's a little bit stronger argument for either of them. Here's the fun thing, though. I think you mentioned this last time. If you can pick one of these parameters to add. Because if you pick more than one, what you end up doing is having two parameters to do the job that only one needs to do for that cell. Right? And which one you pick, if you pick, let's say I pick the top one, you pick the second one, Eric picks the third one, we all look at our log likelihood to see, maybe even AIC, BIC, they're identical. The model improves equally by picking all three. How's that sound for you? Is that crazy or what? Actually, that brings up a point that I didn't actually bring up before. In this directed acyclic graph, if you change the direction of one of the arrows, let's imagine we take this arrow right here, flip it, and we don't have a loop. Now, I don't know, we may have a loop here, so that may completely destroy this. Yeah. Maybe we flip this one right here. Right here. It fits equally well as this. So, what I'm trying to get you to here is why the importance of theory in deciding this, right? From a mathematical perspective, this graph and the model it implies is the same as if we were to change perceived usefulness and flip that arrow over as well. Yeah.
I like how it correlates between two variables in the same mathematic order which you're thinking about.
That's basically it. That's the thing. So, yeah, it becomes a bit of an issue. So let's go here and think about it, right? We've got these are the two pairs of variables where we have those extreme values for the normalized residuals, right? And so, again, we could do three different fixes. We could put an uncorrelated, basically a undirected arrow, one with undirected path, two arrows on the path, or we could put direction on either of those. Okay. Just a little bit more description. Actually, we said this before. So each of these, once again, the modification index value. So this is the change, basically what the likelihood ratio test would be. -2 times the difference in log likelihoods between the model that you currently estimated and the model with this parameter added. And you'll see they're almost identical. These two are identical. That one's off. I have a hypothesis that's because there might be a piece of missing data here that isn't in the others. The expected parameter change is the value that the parameter will become if you add this to it, the expected value. All right, so we know that we had a zero value for each of these before. So really that change is really just what the parameter happens to be in each of those. So for us, we're going to pick to use the residual covariance between usefulness and math self-concept. Right? It's unexplained. The covariance is unexplained by the model. Right? And those were the values of the modification index, 41.529, and the parameter change. So when we put this parameter in the model, we would expect the covariance to be about 70. Right? Now remember, covariance is a weird number. Right? It's correlation with units. So it's hard to tell if that's a big number or a small number. So what we're doing is proposing to add that. Okay? And here we go. So we have to start over with our path model decision tree, right? In the decision tree, we had to kick the computer and then start back. Right? So it is identified. There is no cycle to it. It converged. The parameter standard errors looked quote unquote acceptable. Again, it's hard to judge that without practice. And now take a look at what we have here. This is your overall model comparison with the saturated, right? This is the top. And again, now, in the robust or scaled column, this is the old output. The numbers are the same, but the labels have changed. What this tells us is what, right? So once again, we had 8 degrees of freedom. Where's that come from? Well, there are 20 covariances in the saturated model, and there are 28 covariances in the saturated model. Variance is covariance. 20 parameters in our model. Right? So the difference between the number of free parameters and the one that we have in our model is 8. That's our degrees of freedom. So that is this 14.393 is a chi-squared test statistic with 8 degrees of freedom, giving us a p-value of 0.072. Now, this is a really powerful test. So when you see a high p-value there, that means what?
Significantly different than the saturated model.
That's right. Our model here fits as well as the saturated model. We want this p-value to be large. How many times have you said that in statistics? I can tell you a few, particularly when it comes to dissertations or master's theses. I think I had my master's thesis took 3 experiments over 4 years. It's pretty insane. And I had like 36 test statistics in every different experiment. Finally, one of them hit. Of course, type 1 error rate would suggest one would hit eventually. And I finally got a master's out of it. But I will tell you that was a time I was hoping for fewer p-values, less than 0.05, because there's less things to have to write up. But other than that, apart from me being a lazy student, this would suggest this fits, right? Now, we're still going to look at all the other numbers and see how they do too. Okay? Yes?
So when you report your model, whether it's for your assignment or if it's for a journal, you want to get all of these thinking while we're reading that we did. Say, hey, I've considered various objectives and it just going this particular way of setting fit or not.
That's right. Yeah, we have the whole set of numbers here. The chi-square, this sometimes doesn't get reported because it's usually p-value very small. These are simulated data. It surprises me very little that this is where it needs to be. But the other statistics, RMSEA, CFI, TLI, and standardized root mean square residual, those ones will all be reported almost always. So RMSEA is 0.048. And if you want to see this actually in the new version of R, let me just run that real quick. The new version of Laban, I should say. This one. Ooh, you want to see that? Okay. Of course, it doesn't rescale, so let's do that. There we go. Here we go. Same numbers, right? RMSEA is down below, a little bit different order. So 0.048. So it actually tells us a few things, right? This tells us 0.05 or less for RMSEA is really good fit or good fit. And it tells us, yes, first of all, it's less than that. What is the confidence interval? Actually, this is the confidence interval. Robust RMSEA is 0.053. The not robust is 0.048. So it's sort of in the borderline. The confidence interval goes between 0, which is perfect fit, and not so good fit. That tells you how much certainty you have in your data. And then you end up getting the probability that the RMSEA is bigger than 0.08. So it's a small chance of being bigger than 0.08. And then less than 0.05 actually has a pretty good chance. This is telling us things are moving in the right direction, right? Similarly, CFI is 0.990. That's a good number. You see that, you'll feel pretty pleased. I guess you'd say the robust version. And the robust Tucker-Lewis index is 0.973. That's another good number. So overall, if you got this, I think you'd say, very nice. Questions on any of this? You want to see the value of the covariance that we added? The value is 70.249. And it was very close 70.912 is what was expected. So real close in magnitude to what it needed to be. So the nice thing about that is if you look all the way over to the std.all column, that is the standardized estimate, and the standardized covariance is known as a correlation. So we'd say that this residual covariance, or the residual values between usefulness and math self-confidence, had a correlation, a positive correlation of 0.38. So if we're trying to interpret that, which we rarely do, but if we wanted to, what that means is once we predict usefulness and once we predict math self-concept by this big model, what's left over in each has a positive relationship. So it means we're off in the same direction. Yes?
I want to ask, is there a threshold about how many indexes are we looking at? Now when we consider this step, because in the previous model, only we can identify one, so one is if it's not, but is there a threshold for how many indexes are close before we can consider it?
Oh, you mean the modification indices? No, see, so I would guide it by. I like to guide my version of that by looking at the residual covariance itself, right? So here, I start here, and I look and I say, okay, which one of these is big enough to worry about? What I mean by worry here, meaning these are like z-scores. Which one is at least 3 standard deviations away from 0? 3 or higher. This one's in between 2 and 3. I'm going to use it as a teaching example. So this, for me, narrows my search, right? When I look for where to fit, I know I need parameters that involve one of those cells here. And in just a bit, we'll do the other parameter as well. So that'd be what instead of looking at all the modification indices, I will look at normalized residuals, and then I will go hone in on specific to that cell what I want to fix. Does that make sense? That's a bit better to me because you're right. We get so many modification indices. Let me see if I can. I don't know if I can display them. Here they are. Let me grab the modification indices for model 7 here. Look at all those, right? It's a lot, right? And then we could order it by size. Now, here's the other thing about modification indices. You might say, oh, look, I've got some values on here that are still pretty big, right? I got 6s. I'm going to go and make this quick. I don't have enough time to do it one at a time. Well, it turns out you have to do it one at a time because each of these modification indices is comparing your current model to the model that hypothetically added that one parameter, right? And every time we add a parameter, all these are going to change. So you might say, oh, look, I really wanted to address CC and gender, which is right here. So let's add this one. Oh, but look, CC and HSL is high too. Maybe I should add that one too. There's no evidence in this to suggest you have to, right? Because each of these is one parameter at a time, right? Now, mathematically, and if you're intrepid and you want to code something, you could create a modification index that had more than one parameter, but none of the software that I know of will do that. So it's all is one parameter test. Yes?
Is it essentially like it takes your model, edits it, and then removes it? Then takes your model, so like 20, it's its own.
You would think.
It doesn't then like 26 isn't also included in 27.
Right.
That kind of thing.
That's exactly right. Yeah, you can think of it that way. Now, what's happening behind the scenes is there's mathematical formula. It doesn't actually fit the new model, and that's why it's approximate what happens. But it's exactly that. It's repeating that process. You can think of this as if the machine were to fit 76 different models, that's what would be there. So this is sort of, again, this is almost like a decision tree, right? Oh, I added that parameter. Now I got to go see what I'll add next. And if you pick a different choice of a starting point, you might pick a different parameter next if it still doesn't fit. So, does that make sense? Okay, overwhelmed, anybody? I'm trying to narrow it down. So what happens, you fit a model, if it doesn't fit, you look at the residual covariance for guidance as to why it's not fitting, right? Make note of which variables are involved in that. and then go and figure out the modification indices that only involve those variables. If you choose to add that parameter, start that whole process one more time. Yeah.
Your protocol saying, you run your experiment and everything, say, okay, I'm allowed to add only covariances,
Yes.
but I'm not allowed to add any direction at all.
Yeah, you can do that. Yeah.
Because that's less of a change.
Correct. And this gets into, again, this gets into the, I talked about last time, the replication crisis in science, where we couldn't, one of the hypotheses about why we couldn't replicate a lot of scientific findings is because they were sort of capitalizing on chance. And this is, right? These are extra hypotheses tests, right? So how do you stop capitalizing on chance? Number one, make sure there's a really big effect. This is a big effect, right? Number two, when you look at what happened scientifically right after 12, 13 years ago, now we have a whole bunch of other ways. A lot of journals now want you to pre-register your study. How many of you have heard of pre-registration before? Pre-registration is where you submit your study plan to the journal ahead of time, right? And some journals, there's different levels of how much openness you can have. But some journals will give that registration report almost like you've written a half paper, what your study is, introduction, and then what you plan to do. Some journals will take that, and if they approve that and you follow that, then they are basically saying, yeah, we'll accept your manuscript later on. Now, not everyone's like that. There have been some journals, I've heard lots of stories, I'm sure you may have if you've had to deal with this before, but there are places where you can go online, pre-register your hypotheses, saying, I originally had this hypothesis, and then when you've changed, if things change, then you have to sort of have a plan for how to fix that. And one of those plans could be only residual covariances. In path analysis, those again those are somewhat benign. When we get to the next part of this lecture about factor analysis, they are not benign, right? And so this is where like a little bit of finesse is. But if you're worried about your process, yes, write down what you're planning on doing, and that will depend a little bit on the model. Okay, I feel like everybody's overwhelmed. No? So. It's a lot of information. But let's keep going, shall we? So you would say, Jonathan, stop. This fits well. I just wanted to show a little bit more. Just to say what would happen if we continued, right? Basically, I wanted to give you a second step to the process. And because these are simulated data, they're probably going to fit pretty soon, right? There's the parameter investigation. Actually, let's talk about some of these parameters first. You can go and further refine the model, like if you see non-significant parameters, like this one right here, you might want to take that path out for parsimony's sake. Not a lot of people do at this point because it's just so many parameters going on, right? But if you were interpreting this, how would you do that? Right. So again, in the regression section, there's your outcome. The tilde means it's being predicted by, and there's what's predicting it. Right? And so performance is being predicted by high school courses, math self-concept, and math self-efficacy. And it turned out, of those three, the high school courses didn't seem to have a significant effect. But you would interpret each one of these just like a typical linear regression. Right? You just happen to have 6 linear regressions all at once. Okay? Now, the standardized parameter estimates, those are helpful in trying to decide, again, in standard units. As MSE goes up 1 standard deviation, how much does performance go up in standard deviations? So here the std.all column would say MSE, when MSE goes up 1 standard deviation, performance goes up 0.557 standard deviations, right? Alternatively, if you don't like that, you can use the estimate itself. The estimate itself is in units of the variables. Right? So here, MSE, that's basically for every 1 additional score point on the MSE scale, performance goes up 0.39 score points. Right? And remember, performance was the number of questions correct out of an 18-item math test. So that's saying for every 1 more point that you have in math self-efficacy, your score on the test goes up by 0.13 points. You don't even get a full question right. Yes.
Standard LV.
We're not touching that yet. Yep. That is standardized based on the latent variable, and there's no latent variable here, but it still shows the output. Yep. In fact, if you were to make a mistake about that, standardized.std.lv in this type of model where you don't have a latent variable should be equivalent to the estimate. Right? So probably a misspecification in the Lavon syntax somewhere. Yeah. But it should be. Okay. I just talked about standardized parameters. Not going to talk about that. So overall, this is how we'd interpret the model here, right? We'd say high school experience is a significant. So this is basically going through every regression and describing what is significant. So let's just say it, right? From this study, we found that high school experience is a significant predictor of college experience, right? So more math in high school usually means you're more math in college. High school experience, college experience, and gender are significant predictors of math self-efficacy. Right? So more high school and college experience means higher math self-efficacy. So the more that you do math, the more you feel like you can do math. Men have a higher math self-efficacy than women. So men believe they're more better at math than women believe they're good at math. Maybe an overconfidence there. I don't know. Again, this is 1994 data, though. So remember, this is like a bygone era, shall we say. Yeah. High school experience, college experience, and math self-efficacy are all significant predictors of math self-concept, which means more high school and college experience and higher math self-efficacy. They're all positively related. Higher math self-efficacy means significantly higher perceived usefulness. So the more that you think you can do math, the more you perceive math to be useful. Okay? And then higher math self-efficacy and higher math self-concept result in higher math performance scores, although high school experience was not significantly related to performance. Which makes sense because there's very little heterogeneity in how many courses you take in high school, even in the 1990s, in this sample. And then there was a significant residual covariance between math self-concept and perceived usefulness. Now, I put that there not to interpret it, but sort of to hint at if someone were to come along and want to replicate this, they may plan a study where they think that math self-concept actually predicts usefulness, right? There may be a theoretical rationale for it. But I'm putting it here as a residual covariance to indicate there's something that needs to be done between this pair of variables. Okay? Understandable so far? Just like, it's like linear regression on steroids? No. Yeah. Buff. My kid used to say, when someone would get strong, oh, he got buffed, which I thought was pretty funny. Anyway, yeah, it's buffed linear regression, right? So strong, a lot of it, overwhelming regression. Okay. Finally, then we could also get an R squared for each one of these. Right? So the R squared, remember, there's 6 regressions. Each of those 6 outcomes, we can describe how much variance we're accounting for, right? And how much variance we account for ranges between 0.573 or 57.3% for performance, all the way down to 0.006, or in this case, not even 1% for high school. And again, high school experience, here we go. High school experience, college experience, perceived usefulness have low percentages of variance accounted for by the model. So something is telling us, remember, perceived usefulness was over here on the left-hand side of the diagram. It's being predicted, right? So we can describe why people are good at math, at least on this math test. And we can sort of describe why they have a good self-concept or they have good self-efficacy. But we really don't know what makes a person think math is useful or why they take CC college credit hours. And we certainly don't know why they enrolled in extra math courses in high school. That's what it's trying to tell us. That seem reasonable? I don't know. Okay, now the other thing I will note, another reason why adding the residual covariance is somewhat benign, as I'm calling it, so it doesn't really matter, is that when we added the residual covariance, the R squared didn't change, right? But if we added it as a predictor, R square changes, right? And R square is what people will talk about as a measure of effect size, right? The bigger effect, the more it matters effectively, right? So one other benefit about adding the residual covariance is you have the knowledge in running this model. You know adding that direct effect would change one of those R squareds, right? Either math self-concept or perceived usefulness. But when you add it as a covariance, it leaves them alone. So you're, again, not overstating R squared based on capitalizing of chance, right? Yes, we added the parameter, but we did so in the least harmful way, at least what I'm talking about, scientifically. Okay? All right. Questions? Anybody have questions? Okay. Let's get into something else. There's, in that path model, it's not just everything I just described to you, or what we call direct effects, right? As HSL goes up, performance goes up, right? When you have a big joint path model like this, though, you can come up with indirect effects, right? What is an indirect effect? An indirect effect, I'll just define it. I don't need to put it there. I'll define it. I'll come back to questions later. An indirect effect is one where, for instance, let me walk through it, right? High school experience predicted college experience, and college experience predicted math self-efficacy, right? So if we go back to our path diagram, high school predicts college, college predicts math self-efficacy. Now, high school predicts math self-efficacy, but think of it this way, right? Let's trace some paths here, okay? Math self-efficacy is here. High school has a direct effect of, I'll just use the regular unstandardized coefficient. So for every one additional course in high school, math self-efficacy goes up 4.13 points on its scale, right? That's the direct effect. But remember in the diagram, if high school is going up 1 point, 1 year, one more course, that direct effect is making this go up. But in this model, if this goes up 1 point, there's a direct effect of college. And if college goes up, math self-efficacy goes up. Right? So what we end up having is we have the component of how high school math directly affected math self-efficacy by its coefficient. But what we don't have yet is how it indirectly affects math self-efficacy through another variable that it predicts. Does that make sense? Right? So, yeah, go ahead.
So when you look at this, so because in the output is seen that you have all the direct effects.
That's right.
Right. And so how are you between like what's in that output and like you see like you can always say two different things.
I hear you. But the indirect effect is not automatically in the output. You have to do something to your syntax to get it, right? So the output that you end up seeing right here, these regressions right here, are all direct effects, right? If you want the indirect effect, you can ask for it through syntax, or you can compute it through a calculator. Let's not use a calculator, though. Let's not do that. Let's build it in syntax. But does that answer your question?
Yes.
Okay. So let's think about what that means, right? So here, high school math experience, for every one, let's think what's going to happen. High school math experience, if we add one more course in high school, this number here says we add 0.662 college credits. Now, we have to think, up here we can see for math concept was math self-efficacy, excuse me. For every one extra credit in college, math self-efficacy goes up by 0.393, right? So what we have to think about for an indirect effect, the indirect effect, think of math for it. Let's envision we increase high school math by 1. That means CC goes up by 0.662. And of that 0.662, 0.393 times 0.662 is the indirect increase in math self-efficacy based on high school, right? Does that make sense?
It gives you the amount it increases specifically.
The amount math self-efficacy increases through the indirect mechanism of high school going up, which then caused college to go up, which then caused the component of college that explained math self-efficacy to go up as well.
Nothing much of it for independent variables, yes? Product.
Well, in this case, the math works regardless. They're not independent. This is not like a probability exercise, right? Think of it this way: this direct, so the direct effect here is always in quantities of 1 unit, right? So for 1 unit increase in high school, we got a 0.662 increase in college, right? This number up here says for every 1 unit of college, we get an increase in MSE of 0.393. But we don't have 1 unit that we increased. We only have 0.662, which is why it takes the place or multiplies this number to give us that indirect effect. Does that answer your question? Yep. Yep. It's literally trying to do the math to say, oh, all these numbers are per 1 unit, but in the case of the indirect effect, that's not 1 unit. So we need to put it in that place. I see a question in the back. I think so. Let me. I'm laughing because it looks good on the laptop. Doesn't look good for you. Here it is. There we go. Is that what you're looking for?
Yeah.
So high school math, 1 credit, one unit up here means math self-efficacy goes up by 4. But 1 unit at high school means college goes up by 0.662. And when college goes up by 0.662, math self-efficacy goes up by 0.662 times 0.393.
Can you say that again?
Yeah. Let me put it in more direct terms. The indirect effect is the product of all the direct effects between the two variables. Does that make sense? And why that's the case, again, is because the 0.393 that you see here is per 1 unit of college credit. But when high school math goes up 1 unit, college credit only goes up 0.662. So you're taking the fraction of the 0.393 that's the increase based on college math or high school math. Does that make sense? A little bit better? A little easier? It's a difficult concept. But basically what you're doing is tracing a path. And you're saying, oh, my indirect path represents the effect of one variable on another as mediated by one or more of the variables. This is purely what mediation happens to be, right? If you've ever seen, how many of you have done anything with mediation before? Anybody? And I don't mean legal mediation. But in mediate, I'm sorry, what was that? Oh,
As I say, we did that in general ways.
yes. So mediation, we often, I swear to God, nothing is going to work today. Why? I did, but that was my finger. I want the pencil. But here we go. Finger it is. We have X. We have Y. That's a direct effect, right? We often describe a mediator as mediating the relationship between X and Y. right? And this top portion of it, right up here, go away. That part right there would be the indirect effect, right? So think of it this way. We're trying to say, what we're trying to understand in this analysis is based on our model, there's a potential, and I say potential, we have to check if this number is different than 0, right? But there is a direct effect that we know is significant. There may also be a significant indirect effect. And to figure that out, we have to multiply these two, and we have to do something about their standard error. And that is where the world of mediation has lots of papers and things written about it. If you've ever done them looking at mediation in a literature review, it's a very important, very interesting, and very heavily publicized topic in the methods literature. Because when you make a product of numbers, remember these numbers, I talked about Wald tests before. Right? A Wald test is this number divided by its standard error, and that we compare that with a z distribution or standardized normal. Well, that means, as in maximum likelihood, as n goes to infinity, 0.662 is the mean of a normal distribution. But when you multiply a normal distribution times a normal distribution, you don't get a normal distribution out of it. So there's all sorts of ways to have to deal with this. And I'm not going to get into a lot of them now. But let's talk about what it means, though. All right? The indirect path suggests that the relationship between high school experience and math self-efficacy, if it's not 0, if it's different from 0, but we would say if that's there, then the relationship between high school experience, math self-efficacy is mediated by college experience, or college experience mediates that relationship, right? More formally, the mediational relationship is hypothesized by the path model. A formal hypothesis test is needed to establish college experience as a mediator of high school experience and math self-efficacy. Now, here's the other fun thing. There are a ton of indirect effects in this model. You could be there a while. I'm not going to go down all of them. But there you have it. Let's do some math with it, right? So how we calculate this is the following. It's the product of the two direct effects on the path. Right? Now, in this case, I only showed you two variables. Well, remind me after break what happens if we have multiple mediators in between. The same thing works, it's just more things in a product. But the indirect effect here is the product of these two. So the point estimate of the indirect effect is 0.260. How do we interpret that? For every 1 unit increase in high school, the originating variable, math self-efficacy goes up 0.26 indirectly. That's right. Right? So it goes up, we saw on the diagram, it went up 4 points, 4.1 points directly, but then it also goes up 0.26 points indirectly. And at that point, I'm going to pause here and let's just describe more of that when we come back from break. You're getting extra time for it. We're going to drop a homework after today. I'm going to tell you that much. Question?
This is dimensional analysis.
It is, yeah. It's literally that. It gets really complicated for the p-value. I'll leave this. Yep. All right, so I'm going to pause it here. Let's take 10 minutes. Sorry, I wanted one of our colleagues here in class, again, trying to avoid putting your name on YouTube. Okay, Michael, thank you, Michael, for your permission, had described a way of thinking about the multiplication as sort of in a, what you call it, dimensionality? From chemistry. Hey, my pencil's working. It is. But the way that we were thinking about it is this. We know that for every 1 unit of HSL, CC would go up by, what was the number again? 0.662, right? And really, we want to multiply that through, knowing that for every, we have HSL here, son of a gun. No, I'm just mentally overloaded, and this is what I was telling you all. Things just fall out, like visuals, audio. Thankfully, I ate lunch before I came. I am, showered at least. I think I smell reasonably normal. So at least the basic functions are still there. I'm not over here going to brag. I don't smell good. Let's just say it that way. The basic functions are still happening. It's just it's like I'm the Spirit Airlines of life right now. It's like no frills on anything. You know what I'm saying? Anyway, it gets that way sometimes. It happens. It's part of the fun of life. All right, this is point. So for every 1 unit of CC, HSL goes up. Of course, I am. For every 1 unit of CC, HSL goes up 0.393, right? And so if we're going to cancel things right here, no, not HSL. This is math self. Yep, MSC. So we can't erase HSL. But basically, CC will change, and that what we end up getting here is the product. This is a nice little mnemonic for it, but I thought that was one other way to approach it. But that's the multiplication function of it we have there, right? So once again, the indirect effect, and I'm double checking. Yes, hey, YouTube, I'm recording. That's good. Like I said, the Spirit Airlines of life right now. Just no frills. As HSL goes up by 1 unit, CC goes up by 6.662, and as CC increases by 0.662, HSL increases by, this should be MSE increases by 0.393. That's where the product comes from. So that's indirect, but there's also total, right? Because we know the total effect is the sum of all direct and indirect effects. Basically, this is, when you just come from linear regression, this is what a direct effect is. If you don't have a path model, your regression slope is the total effect in a single outcome linear regression or linear model. But because we have both direct and indirect effects in ours, we want to quantify the total because we're looking at, we might want to characterize what's the overall impact of high school experience on math self-efficacy. So we add together the direct effect and the indirect effect, so we get the total effect. And what that means, how we interpret that is just like a regular slope. For every 1 unit increase in HSL, math self-efficacy goes up by 4.398 points. And if you want to break that down, of that 4.398 points, 4.1 of it was the total. And then the rest of that number in between, 0.260, was the part of increase that was through college experience, because of college experience, effectively, or mediated by college experience. Yeah. I don't know. I personally don't, but that's me. I don't know what the field does. I'm not, so believe it or not, there are methodologists that only study mediation. So I am far from being able to even describe what they know about this. Okay. Yeah. I'm more on the estimation side of business and latent variable models than anything else. So this is a little bit beyond what I can tell you is done. But I would say, for me, it is informative, right, to figure this out. And maybe that is important. In the times I've done indirect effects, I often think the direct effect tends to be much higher in magnitude than the indirect effect. Can I pause for a moment and make a little thought experiment here? Not thought experiment, but. So you see this as a directed acyclic graph, right? There are other directed acyclic graphs that show up in machine learning. Neural networks. Neural networks, you know what I'm talking about with neural networks, right? You have a bunch of inputs, which are predictors. You have a bunch of outputs. We have one output, right? And in between, you've got these hidden layers of nodes. They're sort of variables that are like latent variables that you don't see. And there's direct effects between inputs and the nodes in the middle. But there are no direct effects typically between inputs and outputs. So seriously, you know what I'm talking, I mean, if you're, I'm the Spirit Airlines of what we love life right now. Let's bring up Chrome, put it on the right screen. Just get a neural network here. Here we go. Just want a nice little picture. Nice, simple picture. Now, there are many versions of neural networks. There are many versions of this. This is path diagram, right? This is what you're predicting. For us, this is MSE, performance and usefulness, right? However, these things in the middle, you didn't observe or estimate. And so what you're trying to do is come up with a system that the more layers you have in the middle, you tend to get a little bit better prediction up to a point, right? The more nodes per layer, you get better prediction. But all of it is indirect effects. All of it. And when you think about how much energy and money, now, again, not all architecture runs this way, and there may be network models that work differently. But when I first started doing neural networks and working on them myself, or looking at them, started studying them, my first question is, what are the direct effects? You know, and like, I started learning, I kid you not, I started learning neural networks in 1997. That's how long, like, I had them in undergrad, right? Been around a long time. And like, oh, but I learned it from cognitive psych, where it's like, this is sort of a hypothesized, very simplified version of how brain works, neurons, right? It's hypothesized and overly simplified because there's nothing that stops a neuron far upstream from connecting with a neuron far downstream. So again, it's a simplified version of the brain. But if you think of how much energy, and literally in this country right now, energy prices are through the roof, and part of it is a big chunk of data centers running AI. I just have to wonder. Now, I don't have an answer, but my speculation is, how much better would it get if we added some direct effects to this? Right? Could we get more effective? Anyway, but so to your question, I tend to look at the direct effect in the time. There are people who know better than I do, first of all. But second, in the times I've done mediation, I tend to find the direct effect is much larger than the indirect effect, almost. In the times I've done it, the narrow set of universe of me. How's that sound? All right. Okay. So, how do we do this in Lavon? There's hypothesis tests. We get a point estimate. We can multiply those parameters together and get a point estimate. The problem that we end up getting is that it's hard to see if that estimate is significantly different from zero. Because, as I mentioned before, a product of variables, in a statistical sense, the null distribution product is difficult to derive, right? So what I'm saying is, in a hypothesis test, you're comparing your statistic under the distribution of the null. Well, here we had a null statistic for the direct effect, for one direct effect that's standard normal. We have another one that's standard normal. The product of standard normals is not normal. So the product of standard normals is chi-square. But these aren't exactly that either. They're asymptotic normals. So there's been lots of page space taken on how to handle this. It has become a hot topic. It sort of died down. When I wrote this slide, it was a hot topic. That was like 10 years ago. But yeah, evidently I need to update that. What this test in Lavon I'm going to do is going to use a bootstrap resampling technique to estimate. So bootstrap is not like maximum likelihood in that you find one set of estimates. What bootstrap is doing is basically taking your data thinking that as like the population of cases, and then drawing with replacement a sample from your data that's equal to the size. Now, with replacement, which means if you have, I think we have 300 some observations, 350, I think it was, right? So I'll take that whole 350 and at random draw 350 of them, some of which may be identical, right? And then run maximum likelihood again on it. And then repeat that process over and over again, maybe 1,000 times, maybe 100 times. And then look at the distribution of all the estimates, right? So for every time I take a resample, I get a new indirect effect. And based on that distribution, quantify how far away from zero we are. But that is done behind the scenes. And I'm telling you that because this will be, if you do a mediation analysis, if you start to analyze indirect effects, you will have to describe how you found your p-value, right? And if you just say I'd use bootstrap resampling, it should be okay. There may be other methods that come out, that have come out, or that will come out that you may have to think about, but this should work. But here is how it works in Lavon, how we get it to estimate. Because Lavon will handle that for us behind the scenes. What we have to do, let me start at the bottom and then move to the top. I'm going to define a parameter in Lavon. In a lot of maximum likelihood algorithms, you can do this. Basically, take two or more parameters, make some mathematical function of them, new parameter created, right? This is not a model parameter, so it doesn't count in our degrees of freedom. This is basically a summary of parameters that it will calculate. So here I use the following syntax, colon equals. So colon equals, that is the oddest emoji sign, maybe Punisher, maybe someone with big, like a saber-toothed tiger, like I don't know what that is, but colon equals, and you see that in Lavon, right? Single tilde meant regression or intercept, double tilde meant covariance or variance, colon equals means I'm going to make a new thing, a new parameter. In this case, for indirect and total effects. So I name it, I put a colon equals, and then on the right-hand side, these are labels of parameters. There is no parameter in, if you go to the original syntax I have in my model, right up here, you'll note there is no parameter named BHSLCC. And there is no parameter named BCCMSC. So what I have to do is I have to provide that label. So up here is where I defined all my regressions, the endogenous variables, right? If I go to the MSE line, which is where that indirect effect comes from, I will label the direct effects. A label in Lavon is a character string followed by the asterisk like you're multiplying. And it has to come in front of the variable on the right side. Yes. M plus had like 8 or 9. I don't know about Lavon though. I don't know, but let me tell you how I define this. The B stands for B as in regression slope. Underscore HSL, that's the predictor. And the outcome is MSE. So I have that. That's my own notation standard. You can follow your own for it. I saw another question.
Yes, I think it's just about the code in general and how it runs. Would you have to define that earlier in the code
Turns out you can define it anywhere in the code.
as long as it scans?
Yeah, so it'll scan everything in here. Where the biggest mistake typically is like I always forget to put this in front of the variable name. Like I'll put it behind it. But it can be anywhere in the syntax. So that's at least a little bit more convenient. In M plus, it comes at the very end. There's a set of syntax called new parameters, and it sits in that section. But I'm not going to get into M plus because I'm having a good day. Maybe I'm not, actually. I don't know. It's a pretty good day. Yeah.
Yeah,
Fine.
it's very, very nice day.
It's very no frills, definitely. Definitely no frills. All right. So this is a label for the effect of HSL on CC, right? That's this one. This is the label for the effect of CC on MSE. So this is the indirect effect. Those are the two paths that have to be multiplied. And that star between it says multiply these two, right? This star up here says that's the label of, but in the colon equals line, the asterisk means literally multiply these two together. Okay. And then in the total effect, we add the direct effect of HSL on MSE to that indirect effect before. Okay. So when we do that, here's what we get. In Laban, right here, we get defined parameters in output, and this will tell us the values and their p-values. So let's go down, grab that code. So my syntax here, you'll see I put those indirect effects of interest at the end of my syntax, but you can put it wherever you'd like. And here, oops. The defined parameters are at the bottom of this, oops, bottom of the screen here. Here we go. So what does this tell us? The indirect effect we saw is the product of those two slopes, 0.260. The p-value for that is 0.019. So it is a significant effect. So this is what you would say, oh, college credit mediates the relationship between high school courses and math self-efficacy. That's how you define it. That thing, p-value is less than, is a small number. You use 0.05, fine. That's it. Now, you interpret the effect the same way, right? This is because it's an indirect effect of HSL on MSE. You're saying as HSL goes up 1, MSE goes up 0.26. Now, you can, pardon me? Because of CC. That's right. That's right. And that's in unstandardized units. If we talk about standardized, we interpret it the same way. For every 1 standard deviation increase in HSL, MSE indirectly goes up by 0.029 standard deviations. So it's same type of description. We just have to remember that this is the indirect effect and the mediator here, and what the mediator happens to be, right? Same with total. So the total effect we calculated with slides, but here it is in Laban, 0.4398. 4.398 means what? It means as HSL goes up 1, MSC goes up 0.43 or 4.398 points total, in total. So the total impact of high school courses on math self-efficacy is 4.398 points. Of that, 0.26 is indirect effect through CC. That p-value, again, is close to 0, so that is a significant effect. And again, the standardized coefficient, we'd say the same thing. For every 1 standard deviation increase in HSL, MSE goes up 0.488 standard deviations in total. Right? How are we doing? Okay. Now, before break, I asked you to think about what would happen if we had more than one variable. So here we had x, we have y, we have m, we have j. Now, the indirect effect is what? You have to multiply this path weight times that path weight times that one. Right? So it just gets more complicated as you go further. Yeah. So this is why you will not be doing path analysis for your dissertation, right? I'm just kidding. Period. Ever. Ever. Just think about trying to give you the total effect from a neural network, though. Just kidding. We don't interpret those parameters. Interpretability, who needs that? We just need prediction. Anyway, so our output suggests this indirect effect is significant, so what we say is CC mediates that relationship. Now, when it comes to mediation, and again, in a big path model like this, there could be a lot of mediators. More often than not, you're not outlining them in this whole model. Right? Typical mediation studies that I see don't have that many variables. Right? They're very small paths. So you may get it's possible to get overwhelmed. We're not going to worry about that. We're not doing any more than this, okay? And you don't hear this, and you don't hear this on YouTube, but in my ears, the Law and Order just went through because of I used to have a habit of putting my transition slides with noises to wake everybody up because I need gimmicks to teach statistics. Questions about indirect, total, or direct effects before we go forward? No.
Would you recommend that? I feel like you have three indirect effects that or three mediators, what we say, but each one of those has like its own line to see whether or not that particular mediation was significant or not.
Oh yeah. Oh yeah. I mean, if you have a situation, let's see. I think you're saying this right here.
Yeah, and then you have three paths that are going to y. Then you can do x m, x y, x m y, and x m j y.
Right. Yes. And I can't get that one there. So what ends up happening here is, yeah, you could have this mediational relationship, and if you had that one, you would have this mediational relationship. But here's the hard part: you usually want the total. So what's the total? The total is that path plus this path product plus this path product plus that path product, right? So the total relationship gets much more complicated. Total effect. Okay, another fun fact. Let's take a look at this X to M to J to Y path. By the way, the J is the default letter for me because that's the start of my name. Just because. I was on the fly thinking, what's a good letter here? And all of them didn't sound good. J, nobody's offended by a J. Although, maybe you are. Just hold that to yourself. Okay. I don't know what I'm talking about. I was thinking, like, oh, I'll put an F there. Oh, I know what that stands for. Let me put an F. I can think of all the things it could stand for. J, okay, fairly, nothing. Nobody's going to bother me about my name. All right. The total effect here. Let's imagine that one right there is equal to 0. Right? The M to J direct effect is 0. What does that do to the indirect effect of X on Y through the MJ pathway? It's gone. It becomes 0 because it's a product. So if any of the paths are equal to 0, that indirect effect has to be 0. Now, in practice, as you know, you never get exactly 0 in your computer, in the numbers in your computer. But just hypothetically think, for mediation to occur, there has to actually have to be two non-zero direct effects, right? The direct effect between X and M, and the direct effect between M and Y, right? That's the other thing to think about. Similarly, if you've got a long chain like this, like X to M to J to Y, and the XM pathway is 0, you don't even have to worry about the rest, right? Yes?
I have a question like, when we calculate the indirect effect, like if any of the direct effects on the path like insignificant, do we still like add them?
Great question. Yes, even if they're insignificant, we still want to calculate them. Because, and typically, and again, now this is where someone who's much more experienced in research on the topic will know better than me from practice. But in my typical experience, if this path here was, 0.01, but it was not significant, what you tend to see is this entire pathway is not significant. But it's not always the case. It can be, it can be the case that you can have a really massive one here and a very trivial one here, and the massive one sort of compensates for it. It's not, I guess it's compensate isn't right. It overwhelms. Compensate is usually an additive relationship, not a multiplicative. Yeah.
Question related to
Mm-hmm.
multiplication, like you introduce like essentially maybe step one as method to maybe add either covariance or covariance or direct effects. I'm curious like whether we should also like have some method to train the model, like remove some effects with the step one or like with just record significant path
Yeah.
redo the model.
So you can think about that in theory, right? The more zero paths you have, you take power away from the other effects. All right. So what do I mean by that? In practice, if we look at here, there is a very close to zero pathway there on the HSL predicting performance, and a very close to one of gender predicting HSL, right? And those are two model parameters that effectively probably can be removed that won't change a lot. What do we gain by it, though? A zero parameter does not bias our model. So bias is not an issue. Right? Bias meaning we don't get wrong estimates because something is zero in the analysis. What we do happen to have is this takes away power to detect the other effects. Right? So we may lose a little bit of power per every additional parameter we get. So the other thing we gain by it is protection from, even though it's zero or statistically zero, that number not being zero means that covariance between these two has a non-zero value. So model fit gets potentially slightly improved by including them. So it's an interesting thing. You often hear, especially now because of regularization, have you guys heard of lasso or ridge regression regularization techniques? There's a bunch of, I think they fall under machine learning, but they came from other purposes. When you have a lot of predictors in a small sample size. In the 1990s, very famous statisticians now came up with a way to model that by changing your least squares formula to sort of penalize the model based on additional terms. So what it ends up doing is sending some of these things straight to zero, right? And you'll hear editors and reviewers and say, oh, stepwise regression, don't do that. Use lasso. Use a right here. I don't see that much here. There's not a need for it. Like if you look at the sample size we have versus the number of model parameters we have, it's not big, not a big difference. And there's not likely to be a bias because we have so many parameters. So to answer your question is, I often don't think of model reduction as being needed, particularly if you have a well-crafted model to begin with. If you're sitting there thinking, I don't know what the relationship is, and you throw in every path that you can, that's a thought where, yes, you probably would want to do some type of model simplification. Stepwise is one way. Lasso, something along those lines would work as well, too.
Yeah, like I had this one minute, what if like I use like literally to like calculate the parameter the bias and actually run this,
Yeah, no, I think by and large, in a situation where you have a fairly limited number of predictors, right? Any one variable at the most has 3 predictors. That's not a lot in this example. Probably not going to matter. If you have a situation where you have 20 variables and one of them is predicted by 19 of them, and your sample size is 100, you're getting into a spot where maybe you need to worry about that, but probably not for us. But I will say, I think the polite way of saying is reasonable people may disagree. I think Lisa says that sometimes. And I think that's a nice way of saying they're wrong, but they're going to keep believing this. No, I would say that you hear this a lot. You hear, oh, you got to worry about these predictors. Like a zero predictor is not a bad thing. It takes away a bit of power for the other tests in a multivariate model, but it's zero. Fine. Yeah, that's what typically happens, right? And actually, in the Lasso's case, it's a little more complicated than that. You have to, the penalization term is not estimable, so you have to try multiple versions of it. And then you have to go and figure out which one you like the best. And then at that point, you can take those regression coefficients. I suspect there are probably path model analyses that involve a lasso as well, too. People probably put that there. Lassos everywhere these days. I say most likely not needed. If you're in a spot where you have a lot of variables, shoot me a note. I can send you an email about some references to look at. But most of the time, no, don't do it. Other questions about this? Complicated topic, huh? Is this a complete repeat of what you learned in generalized? Good refresher, or is everything that you in here also in generalized? Am I just repeating it or no? Okay, so this is much more. Just making sure I'm not just being like wasting your time. Okay, okay. All right. My Spirit Airlines would like to move to an upgrade. If I'm wasting your time, I'm like, well, I don't know how I'm going to unwaste your time, but we'll figure that out. Not to say there's anything wrong with Spirit, you'll still get there. Hopefully, it's safe, right? Safely. So, in many ways, uncomfortable but safe is better than unsafe. Anyway, all right. So, this are just the last details here. In the analysis we just ran, it was meant to be an introduction to the topic and the field, and it's way more complex than I just described. Right? You can go on rabbit holes. This is a well-studied topic. And yes, just because causal inference rediscovered directed acyclic graphs doesn't mean they haven't been around for over 100 years in this format. Right? That's how long this path analysis has been around, like 1915, 1911, like long time, right? So there's a lot of a research study base to it. And this analysis you saw here, we assumed all variables to be continuous. We knew that wasn't the case because there was a dichotomous variable there, and multivariate normal. Well, I generated the data so they're multivariate normal, but when you collect your data, you don't get that benefit, right? You don't get to say, yeah, this is multivariate normal. In reality, neither of these are true. The other thing I will talk about is we also assume perfect reliability for all of our variables. What does that mean? That means when we put the sum score in, it has no measurement error. I haven't defined measurement error yet, but basically think of it as instrumentation error, right? If you're trying to measure the width of a door, because if you're like me, you might be moving, right? You got to get your furniture in the house, and your ruler has unequal inches on it. Your tape measure has unequal inches on it. That's measurement error, right? Anything that's could be a construct or a survey, or that's math self-concept, something we can't directly observe, is not likely to have perfect reliability. So that's also violated. And structural equation models, which are, again, path models with latent variables, that will help with variables with measurement error. When it comes to the multivariate normal or the continuous data assumption, you can find different distributions for the variables and build it there. The problem is, typically, with the exception of, M plus has a lot of distributions. Levon has like categorical data, ordinal categories. After that, I don't know how Stata's SCM package works. What would I recommend, Erica? You've been in my classes. Stan, Jags, yeah, you name it. I'd be like, oh, just throw it in the Bayesian system. And you're going to sit there and go like, I need to graduate, right? So maybe not Bayesian, but the point I'm trying to make is if you find yourself in a situation where you're worried about this, there are remedies, but this doesn't fit into this course. Okay? And then causality. Oh, causal. It's funny because before causal inference was super huge, when I was an undergraduate, my professors in the 1990s were saying, these path models, they really can detect causality. I'm like, no. They're just a bunch of simultaneous linear models, right? And the same thing that you would claim about a linear model and its relationship to causal effects is the same as a linear model with six outcomes, right? So we had in this study observational data. There was no experimental condition. The paper that we were following collected 350 observations of people and didn't put them into groups. They just gave them a bunch of surveys. Hopefully, paid them for their time, or maybe they got course credit. Yeah. So really, causality starts with design, right? Experimental designs help, but don't get you there because random assignment, you may get by chance mismatched groups, right? It may happen depending on your sample size. That's where the causal inference world starts to try to correct or worry about that. So for us, we're not claiming anything causal. We're just saying the same thing happens. So what I would say about the path models and when you're looking at what I showed you today is that the best you can say is that if your model fits, then causality is one reason for it. What do I mean by that? As I mentioned, this right here is implying you're sort of sketching this as if you knew what causal was, right? High school math experience may cause better increase in performance, right? Or college math experience causes your self-efficacy to go up. That's what you're sort of hypothesizing. Your design doesn't allow you to fully say that. But similar to that, why I say causality is but one of those reasons. If this fits well, that's great. But I mentioned before, if I switch the direction of one of these paths, it fits equally well. And now you have two models. Which one is the causal one? Can't tell, right? So when it fits, your claim could be, this could be causal, but really what do you need to go and establish its causal order? Well, first, it'd be great to have a design where you manipulated something. Sure, randomly assign gender. Can't do that, but maybe you could randomly assign college credit. Actually, it's funny, I say that, but I remember certainly it's possible today a little bit better with avatars and no, seriously. I remember there was a professor from Virginia many years ago. He gave a talk. It was like 20 years ago, and it was at the beginning of facial recognition, and he had a way to like he really was proud of himself. He was like, I'm going to randomly assign the sex of a subject. So then, like when someone's speaking to, it was really important about like gender dynamics or whatever, and male speaking to women, women to speaking to men, women speaking to men, male to male, whatever. And he was like, but we're all going to do it with video calls because the subject I'm going to go and mask their face and their voice. And it only got so far because face and voice are only two indicators of gender or sex, right, of a person. There's many more: mannerisms, speech patterns, et cetera, et cetera. But yes, you have a better chance these days. But the point I'm trying to make is really what you need to do is to come up with some type of experiment. And even then, that may not be enough. You may need additional analysis steps to really establish causal features. Okay. Well, I told you I was going to model some more stuff, but I'm not. I'm actually done with this lecture now. It was the longer version of this lecture where I modeled the next effect. But so I don't want to start the next lecture. We've got 10 minutes till break. I will start the next lecture after break. But in this 10 minutes, do you have any questions? And if not, can I show you what happens if I change the direction of a path? You want to do that? Okay. First of all, do you have any questions? I hope you're not asking, why are you here? I would accept it. I would also say, if it sucks, you can vote with your feet, right? But no, I don't. I hope I've made it worth your time to be here. Let's put it that way. Let's take a look at this full path model here, model 7. And the number I really want to take note of is the following. I want the log likelihood user model right there. Right there. Now you can't see that very well, though. I'm just making a note of it. Okay? All right. Let's go and change. Let's make sure that the path I'm changing Makes sense. Oh, actually, you know what I can do? Let's take this covariance, this estimated covariance off between usefulness and MSC, and let's just put MSC on usefulness. This is the different, let's pick the different parameter. Okay? All right. Log likelihood user model. Very close, though. Very close. Yep. And that's what I'm sort of mentioning. And then, though, I wanted to go and show R squared. Now that's where, darn it, I keep doing that. The R squared for usefulness is 0.178. It was 0.04 before. So if you added that path that you had found after your model didn't fit, you just explained usefulness a lot more, which is possible. But we're potentially capitalizing on chance to do that, right? And so you might investigate this, but the reality is, if we were to compare these two models, they're virtually indistinguishable based on model fit. You've got a little bit of small change in log likelihood. If we had complete data, I don't even think that would be there, though. So I think that's. So what I did was I changed. Come on, template. Right there. I took this undirected path, this double-sided arrow, and just made it a straight direct effect. Right? So I didn't. So both of these are still endogenous, but I just changed the nature of that prediction. So everything okay there? Other questions?
Can you go back to the syntax that you changed?
Yeah,
Just
absolutely.
okay.
So here, I had to put a 0 back on that covariance. That was the way it was originally. And then I just added a variable, that variable to the usefulness. Is that what you wanted to? Great.
I just have the original, so I wanted to see how it changed.
The other thing I will note is we have homework on this subject. You know what? Instead of going to icon, how about I just pull up the homework file? The homework is due next week, so ignore the date at the top of this. Oh, that was me when I had the original order, thinking I could get through this lecture in like one day. Missed that one. Oh, I had high hopes already. Always have the high hopes, and they always get crushed. So you got a week to do this. Basically, it gives you data. I found another paper, and try to mirror that. I created simulated data. One thing I will note is in each section, there's a guide. Log likelihood for H0 is this. So that tells you that you're close to the right, you're likely the right model. Why I say likely? Because again, I think these data are complete. I maybe, there is missing data. So it may be the case. You want to make sure when you fit a model and you look at your output that is log likelihood user model here, that number matches the number in homework. Because that will be your check. Now, with 10 people, honestly, the homework system takes longer to build a homework, like Lisa's homework system. I used to run that. It takes longer to build a homework than do it. So this is my green box. When you run the model, check that. If it's there, that's your green box. If it's not, the model's not right. Don't do those steps, okay? Because you'll analyze the wrong numbers. If you try to fix it and you don't succeed, that's where I'm here to help. Erica, Young. Any of us welcome your questions. It's my job, and again, they're paying for the benefit of answering your questions, so make it worth their money. I don't know if that's the case. I hope I think your tuition's been waived. I think they send those things. But point being, if it wasn't waived, you'd be literally paying to work. The reverse internship, the volunteer. No, I don't even know if that's. I don't even know what that is. But anyway,
Teaching.
student teaching. That's it. There's got to be a word in the English language for where you're paid to go and benefit the party. You're paying for the benefit of the party. I don't know. Anyway, paying for the experience, I guess.
The privilege of working for us.
That's it. Okay, so the questions in all this are the ones that we went through here. Like, oh my gosh, come on, Jonathan. Was the model just identified? What are the fit statistics, and so forth? But my hope is that there are 4 models. I'm hoping that the hardest one will be number 1, and then after that, it'll be copy, paste syntax, and make minor modifications. Okay? You've tried it. Not too bad. There's always ways it can go wrong. If you don't get your data in, it's real bad. But I think you should have everything you need to complete it. But I will be around. My office hours again are Mondays, now 1 to 3. And again, please check the link I put in the last announcement on my schedule, because my Spirit Airlines semester also has a lot of things that are like bumping my time that are out of my control. So I will have office hours every week. I will make an announcement most weeks, but there may be something that pops up on Monday morning where I'm like, oh shoot, too late to announce, got to cut it short. I'll have that in office hours. Okay. Okay. On that note, how about we take 10 minutes now and we'll come back 2:30 and begin again. Thank you.